Hi. In this video, we're going to extend our discussion of Gaussian elimination with a focus on the use of a simplified notation and simplified methodology for working with systems of equations, rather than the fully explicit work with systems of equations that we covered in the previous video. So we've seen how we can write linear systems as a system of equations, and the form we have presented here is the most general form we can write for any number of m equations and any number of n variables. We can always write it in this sort of form as a set of individual equations. We've also discussed how we can write this same system in a simplified matrix notation. This system can be written as AX equals B, where A is an m by n matrix that contains only the coefficients. X is a length n, or n-dimensional vector that contains only the variables, 1 through n. And B is a m element vector that contains the right-hand sides. I'm now going to introduce the idea of representing this system as an augmented matrix. An augmented matrix really simply defines a new matrix that starts with A and adds one extra column, an extra column that contains B. A has m rows, as does B, and so this is sort of a well-defined matrix. And m will have exactly one more columns than the number of variables. M contains only numbers or symbolic constants. It contains the coefficients of A in the first n columns and the right-hand side in the last column. It does not explicitly contain any of the variables. Now, M isn't the system. M is just a matrix of numbers, but it contains all of the information built into the system. Right? If we think about it, really what we're doing in writing an augmented matrix is saying, I know I have a system of equations. I know that a system of equations has n variables. I know that it has a right-hand side with a single number on the right-hand side and an equal sign right before that. And I'm going to just avoid rewriting those same variables every single time, the equal sign every time, the addition signs for adding every term. And this simplified notation makes work, especially by hand, clearer, because you don't have to have all of this extra text buried in your work. It makes it faster because you don't have to write out all of the variables in every equation. This is especially true for large systems, and less even physically painful as you get less cramps from doing the writing. The way we work through the elimination process using an augmented matrix like this is absolutely identical. Right? The process is the same, the rules are the same. The only difference is that we're keeping track of the information in a slightly more compact way. Right? There are other reasons why the augmented matrix is a nice way of working with things. There are deeper connections that we'll get into later on, but for the time being, we can think of the augmented matrix purely as a simplified representation of a system that is easier to work with. I really recommend for almost all problems, work with the augmented matrix rather than a system of equations. At least after you get through the familiarization phase, getting used to it, it will become much, much easier working with them. I'm also going to formalize our notation and the way we talk about the rules for performing Gaussian elimination. This will also allow us to, in a more compact notation, in a more simplified notation, carefully explain what we're doing without having to write out explanatory sentences of how we're working through the process of Gaussian elimination. Both forward elimination and backward substitution fundamentally only ever really involve three things we do to the equations in a system. At the core of both techniques is the addition of a scalar multiple. We add a scalar multiple of one equation to another, and we can represent that, and after doing so, replace the one we added it to. We can represent this in the following way. Ri plus krj replaces rj. So if, for example, we wanted to think about the process of, say, let me just write this here, of, say, subtract row 1 from, oops, sorry about that, go back here, from row 2, what would that be? It would mean we're taking row 2 minus row 1 and put that result back into row 2. Okay? One of the fundamental things we do, and actually the core of much of what we do with forward elimination and with backward substitution. At times, particularly in back substitution, when we're trying to solve for a specific variable, we use scalar multiplication of a single row, simply scaling that equation. We can represent that by the expression k times row I moves into Ri. That is, we replace row I with the scalar multiple of that row. And the final thing that we do is sometimes we need to swap equations, swap rows. Call this a row exchange. We use the notation Ri and Rj are exchanged. This gives us a shorthand for keeping track of the different things that we can do, the different manipulations we can do to a system of equations in the process of elimination. Now, with the definition of an augmented matrix and this simplified notation, we can now see how this works in a example of trying to solve a system. Here's a 4-variable system, 4 equations in 4 unknowns. These larger systems, where we're using variables with subscript notation, are really where the simplification of working with things in the context of augmented matrix really helps a lot. So how do we do this? The first step in working with an augmented matrix is to take this system of equations and recast it as an augmented matrix. It is really as simple as writing down the coefficients and the right-hand side in a matrix form. The only thing we need to keep track of is to remember that all of these places that have a variable by itself should have a 1 in front of them. Once we do that, we take the first column of the augmented matrix is the coefficients in front of x1. The second column of the augmented matrix is the coefficients in front of x2. The third column, the coefficients in front of x3. The fourth column, the coefficients in front of x4. And the final column is the right-hand side, which in this case I have set up as all zeros. This is a special kind of linear system known as a homogeneous system that we'll dig into more later in the semester. This is all it takes to rewrite the augmented matrix. Just fill in the coefficients alone without any of the addition signs, without any of the variables, and so on. This has all of the same information of this system. We can rewrite this simply as anytime read this equation as x1 plus x2 plus x3 plus x4 equals 0. All of the same information. Now that we have things cast in an augmented matrix, we can move forward with Gaussian elimination. I'll walk through the steps a little bit more carefully, but we're highlighting how we do them here in a more compact notation of this formal notation of how we replace rows. Gaussian elimination always starts in the top left and moves down and to the right. So how does this work with an augmented matrix? The upper leftmost entry in the matrix is our first pivot. We want to use this pivot to eliminate, or rather set to 0, all of the entries below that. How are we going to do this? We're going to do this with a series of replacements where we replace row 2, row 3, and row 4 with the addition of a scalar multiple of row 1 to each of those. So row 2 minus row 1 gives us is our new row 2, which will eliminate this position. Row 3 minus 2 times row 1, because we have a 2 here and a 1 here, will be our new row 3. Row 4 minus 2 times R1 will give us our new R4. Working through that, 1 minus 1 gives us 0. 2 minus 1 gives us 1. 3 minus 1 gives us 2. 4 minus 1 gives us 3. And 0 minus 0 gives us 0. For the second row, 2 minus 2 gives us 0. 2 minus 2 gives us 0 again. 3 minus 2 gives us 2. 3 minus 2 gives us another 2. And 0 minus 0 gives us 0. For the fourth row, 2 minus 1 gives us 0. 1 minus 2 gives us -1. 2 minus 2 gives us another 0. 1 minus 2 gives us another -1. And 0 minus 0 gives us 0. One of the really interesting things about homogeneous systems is because we start with all zeros, when we go through the process of Gaussian elimination, this last column always is going to stay zeros no matter what we do. Right? Okay, now, what would we do in the next step? We've completed a first column of elimination. We now have a column that has a single pivot. Sorry about that. That has a single pivot and otherwise is all zeros. Very important to note, when we're working with an augmented matrix, when we eliminate things, we replace them with a 0. We don't just make them disappear the way we can do in a system of equations form. This is the one case where there's a tiny bit more writing involved in the augmented matrix, but it balances out in favor of augmented matrix, definitely. So we have a 1 with all zeros below us. Then what do? We move down and to the right, and focus our attention in this kind of remaining subpiece. Second row, first non-zero entry is our pivot. We want to use this entry as a pivot to eliminate the rows beneath. We actually see that this second entry already has a 0 in place. We already have a 0 here. This means we don't actually have to do anything. The formal notation, we still could, however, say, let's take row 3 and replace 0 times R3 with that. Right? Corresponds to doing nothing because we're subtracting 0, but there is a way to formally write it. We can also just think of skipping this because there's already a 0 here. Already a 0 here, but we do need to eliminate the entry in row 4. There's a -1 here. How do we get rid of that? We get rid of that by having a new row 4 that comes from row 4 plus the second row. Right? Executing on that, -1 plus 1 is 0. 0 plus 2 is 2. -1 plus 3 is also 2. And 0 plus 0 is 0. Right? This now gives us our next step. What do? We move down and to the right. Verify. We now have one column that's an entry and all zeros. The next pivot down a row and over a column also is all zeros below. We've successfully got rid of this. We now do the last step of forward elimination. We identify the pivot in row 3, the first non-zero entry in row 3. We use this to eliminate down. How do we do that? The numbers are the same, so we just take a difference of the 4th row and the 3rd, row 4 minus row 3, to replace row 4. When we do this, 2 minus 2 is 0, 2 minus 2 is 0, 0 minus 0 is 0. You might have noticed even beforehand that this last and second last rows are the same. These two rows are identical, and so when we take the difference, we're going to end up with a full row of zeros. We don't delete this in the same way as we do with a system of equations. Remember, the matrix, the reason that the matrix has all of the information is because we have the right number of rows and the right number of columns, and we keep track of everything appropriately. So we need to leave this in here, but we're going to ignore it from everything else we need to do. Right? We have an upper triangular form. We have with our pivots in 3 positions, a pivot variable here, a pivot variable here, and a pivot variable here. All right. Now, we have our upper triangular form. Nothing more we can do with forward elimination. Another way we describe this is as row echelon form. A row echelon form is one where every pivot variable has only zeros below it and only zeros to the left, which is sort of true here. Right? I might use U, and the Tucker book frequently uses U to represent a matrix in this upper triangular or row echelon form. Okay. We've gone now through forward elimination with the augmented matrix. What do we do then? Well, there's 2 approaches we can take. We can, once we've done this, recast our upper triangular form back as a system of equations. Right? We've done manipulations with this exactly in the same way that we did manipulations with systems of equations for elimination. And so the translation back is exactly the same as we used to build the initial system. The first row reads x1 plus x2 plus x3 plus x4 equals 0, as written here. The second row reads 0 plus x2 plus 2x3 plus 3x4 equals 0. This reads as 0 plus 0 plus 2x3 plus 2x4 equals 0. And this reads as 0 plus 0 plus 0 plus 0 equals 0. Once we've recast as a system of equations, we see that we have a 0 row that we can basically just get rid of and ignore. And we can perform back substitution exactly the same we did before. Here I'm going to be a little bit sort of more formal in thinking about how we do the back substitution, right? Using the same language of pivots and these row operations that can substitute. We can cast this back substitution problem as, first of all, looking at the last equation, focusing on the first non-zero element, the pivot, and using this as a pivot to eliminate up, to eliminate x3 from the entries beforehand. How would we do that? We would take R2 and subtract R3 because they both have 2x3. For R1, for equation 1, we would subtract half of the third row, or the third equation from that, and replace that. Right? Because we have zeros down here in the fourth row, we have 0 minus 0 stays 0, x2 minus 0 stays as x2. But 2x3 minus 2x3 gives us a 0 here that we can just ignore. Just to be clear, we really also had zeros in here, but we don't need to be explicit about them. And 3x4 minus 2x4 gives us x4. 0 minus 0 gives us 0. For the first equation, we're going to subtract half of R3. x3 minus half of 2x3 is, of course, 0. x4 minus half of 2x4 is also 0. And so that's the system we're left with. Right? As always, after using our focusing on the last equation, what have we done now? We have successfully taken this variable, and now it's missing from all of the values above. It's been isolated in a single equation. We move up to the next equation, focus on the pivot of that equation, and try to use that as a pivot to eliminate the equation above. Same coefficients, so we simply subtract row 2 from R1 and replace row 1. Right? x1 minus x2, x1 minus 0 is, of course, x1. x2 minus x2 is 0. 0 minus 0 is, of course, 0. 0, remember there's that implicit 0 here, minus x4 gives us negative x4, and 0 minus 0 gives us 0. We now have successfully isolated not only our third variable, we've also isolated our second variable and our first. These variables, the pivots, exist only in one equation. We have another variable here. This variable we could not eliminate and isolate in a single equation because it is not a pivot. This is a free variable. When we have a free variable, we write the solution as pivots in terms of the free variable. But after we've gone through these elimination steps, we can really easily do that. X1 minus x4 equals 0 means x1 equals x4. x2 plus x4 equals 0 means x2 equals negative x4. 2x3 plus 2x4 equals 0 means x3 also equals negative 4. As before, we can write this in parametric form, setting that our free variable x4 equal to a parameter such as t, and then we have the quadruple x1, x2, x3, x4 is t, negative t, negative t, t, where t can be any number. The solutions to this system of equation have the very simple form that the first and fourth entries have to be identical, the second and third entries have to be identical and negative of the first and fourth, and as long as that is true, the actual number can be any number. Right. That was using the augmented matrix for forward elimination, but then recasting back to system of equations with an augmented matrix. We actually don't need to do that. We can stick with the augmented matrix all the way through back substitution, and there's some very, very important results from linear algebra that come from this framework. Let's think about what we're really trying to do. We're trying to isolate every pivot and make a pivot exist only in one position. That we want to isolate each pivot variable. This should not say free. We want to isolate each pivot variable exactly as we do in equation form so that we can write that in terms of the free variables. How do we do that? What does it really mean when we isolate that? It's making each pivot entry the only non-zero entry in its own column, isolated from all of the rest. We also want its coefficient to be 1 so that we read that as x1 equals something, x2 equals something, rather than as a coefficient times the variable. This is our goal. It will become a little bit more clear, I think, if we work through the example. So let's take the upper triangular form that we got after forward elimination in augmented matrix form and apply back substitution in the context of the augmented matrix. Back substitution, we start at the bottom and move up. We begin with the bottommost row. We say there's no pivots. It's all zeros. So we move up and consider the next row. We take this next from bottom row. We choose the first non-zero entry, the pivot in that row, and eliminate upwards. How do we, sorry, getting a little bit ahead of myself. We can do this. It will make it a little bit easier, and the usual way we do this is we're going to, before doing that step, we're going to take one simplifying step here. Right? Note what we have, and I will erase that pen just so that it's a little bit clearer here. Right? We're still going to take this same initial step, of course, and identify that the first row, the bottom row is all zero, so we want to move up. Before going ahead and using this entry as a pivot, before deciding what subtractions we're going to do, we're going to scale this row. We're going to scale this row to make the entry 1. There's two reasons for doing this now as opposed to later. Right? We ultimately want this. We ultimately want to have a coefficient of 1 in front of every pivot. Right? So this is certainly something we might want to do at some point. Why is it good to do it now? First of all, how do we do it? We multiply this row by a half, very simple, and we get 0, 0, 1, 1, 0 instead of 0, 0, 2, 2, 0. The advantage of having this pivot now being a 1 means that the scaling factor we need to use this to eliminate upwards becomes a lot easier. It's just this number. Right? We have a 1 here. How do we eliminate the 2? Well, by subtracting 2 times this row. We have a 1 here. How do we eliminate? We do it by subtracting 1 times this row. So having the 1 here simplifies the scaling factors that we need in this elimination step. R1 minus R3 to replace R1. R2 minus 2R3 to replace R2. Because we have zeros here, 1 minus 0 is 1, 1 minus 0 is 1, 1 minus 1 is 0, and 1 minus 1 is 0. 0 minus 1 is also 0 for the first row. For the second row, 0 minus 0, 1 minus 0, 2 minus 1, 2 minus 2, because we're scaling by 2, is 0, and 3 minus 2, because we're scaling by 2, is 1. And then a 0 minus 0 in the last column. After doing this, the pivot in this third row now sits in a column of everything else being a 0. We've eliminated all of the other variables and converted that pivot to 1. Okay? After doing so, we move up a row. So we're now going to be looking at the second row. We choose the pivot of this entry. It's already a 1, so we don't have to worry anything about scaling. We eliminate upwards. How do we do that? We do that by subtracting the second row from the first. 1 minus 0 is 1. 1 minus 1 is 0. 0 minus 0 is 0. 0 minus 1 is negative 1. And 0 minus 0 is, of course, 0. We now have successfully eliminated the other entries in this column also. So we have a 1 and all zeros, a 1 and all zeros, and in the upper one, we still have our 1 with all zeros. This concept that every pivot has a 1 as its coefficient and zeros everywhere else in the column is representative of what we call a reduced row echelon or a row canonical form. Right? This is as far as we ever take back substitution. When we have an augmented matrix in this form, we are ready to write the solution very, very simply. Why? Let's think about how a translation of this reduced row echelon form reads. The first row, x1 plus 0 plus 0 minus x4 equals 0. x1 minus x4 equals 0. The zeros we can skip when we translate into a system of equations. Skip the first, x2, skip plus x4 equals 0. Second equation. Third equation, skip, x3 plus x4 equals 0. And the last equation is the trivial 0 minus 0 that we can ignore. This form is already almost solved. The only thing we have to do is to move the free variable over to the other side, and we have our answer. Right? So this reduced row echelon form represents an almost complete solution. If we actually had a unique solution, we would in fact have the solution sitting there right in our reduced row echelon form. Right? I want to spend a couple of minutes just sort of clarifying some terminology, because there's multiple words that are used for the same thing, multiple terms that are used for the same thing, and I don't want to confuse you on that. The general result after forward elimination on a matrix is called a row echelon form or upper triangular form. The pivots, that is the first non-zero entry in every row, has zeros below and zeros to the left, but may well have other things above it and to the right. These first non-zero entries, these leading entries in each row, are known as the pivots, the pivot variables. After back substitution, the general result after back substitution is called a reduced row echelon or a row canonical form of the matrix. In the reduced row echelon, the pivot entries are the only non-zeros in each column. Not only do they have zeros below and to the left, they also have zeros above them. In addition, these pivot entries all are equal to 1 rather than any number. All right. These are some of the terminology about the class of matrices that we get after forward elimination and back substitution. You also might see some different terms used for the elimination process. I've been using the term Gaussian elimination to describe the full process, and I've broken this down into forward elimination and back substitution. Sometimes people use Gaussian elimination to mean what I've been calling forward elimination, only the forward steps. And then they use back substitution as a term for the other piece. The complete forward process of forward elimination followed by back substitution, the complete process, is sometimes called Gauss-Jordan elimination. We'll see that the same algorithm can be used to invert a matrix, which always is called, or almost always called, Gauss-Jordan elimination. But sometimes Gauss-Jordan elimination is also used in the context of just solving systems. Gauss-Jordan elimination always means that back substitution is included. Gauss-Jordan cannot mean only the forward steps. Elimination by pivoting is not a term. It's used a little bit in the Tucker text, and this is why I'm mentioning this. It's not extensively used outside of that. You'll see some other context saying Gaussian elimination by pivoting. I'm going to avoid using this term, especially because there is similar language that is sometimes used in the context of numerical linear algebra. And that similar language can confuse, for different processes, can confuse things, I think, when we use this term. I will call things Gaussian elimination and occasionally Gauss-Jordan elimination. Okay. So we've gone through examples, and I've tried to demonstrate how we do things and explain the rules. One of the really nice things about forward elimination is that we can actually write down the rules rigorously in a mathematical framework that then can be used to write a computer program, for example, that would solve the problem perfectly. Right? It's also a set of rules that we can sort of follow in solving small problems by hand, just sort of following the process step by step without really thinking about what we need to do. I'm not going to spend a lot of time on this formal definition, but I do want to demonstrate how it works. Right? Remember, this was our general framework. We begin with the augmented matrix. We're going to work from top to bottom, left to right. And in each step, we're going to use the first non-zero entry as a pivot to eliminate things below, move to the second row, repeat that, and so on, until we get to our row echelon form or upper triangular form, with a caveat that sometimes we need to do a row exchange. we can write this in formal notation like this, as kind of an algorithm, working with an m by n plus 1 augmented matrix. So we have an extra column, A with B as a last column, and A being this matrix of coefficients. We're going to start with I equals 1 and j equals 1. In the first row, first column. And we're going to repeat these steps until I becomes 1. One of the things we're going to be doing is increasing y, right? Or we can stop once all of the rows below I contain all zeros. They are equivalent statements. Then what are we going to do in each step? We're going to ask, first of all, what is Aij? Remember, in the first step, this is A11. If it is not 0, we use it as a pivot to eliminate that first column, that column j, for all rows below it. That is for all k, from I plus 1 up to m. Then, after eliminating that, move to the next row and column. How do we write that? We write our replacement rule, rk minus our ratio of the coefficient on row k and the coefficient of the pivot multiplied by row I, replacing row k, for all of the rows below. After doing that, we make j increase by 1 and I increase by 1. This is what we do if we have a pivot. If our pivot is 0, we check to see if there is a k below that, a row below that, that has a non-zero entry there. If it does, we exchange rows, right? And go back to this step and continue. If both entries, if the pivot is 0 and all of the entries below it are also 0, we have no pivot in that entry, then we move to the next column. We don't change the row, but we move to the next column, and we go back and we try to move forward again. This is a formal notation that can be directly translated into computer language to execute forward elimination. It's important to remember that there are some checkpoints with forward elimination. If you're doing this computationally, or if you're doing this using these rules by hand, after forward elimination or during forward elimination, you should apply these checkpoints. If you get rows that have a non-zero entry only in the last column, these correspond to equations of a form 0 equals something, where that something isn't 0. It means that the system has no solution. Stop. Stop. No solution. Do not proceed to back substitution. If we have fewer non-zero rows than variables, that is, we have fewer pivots than there are variables, that means we must have columns that are not pivots, that other than the last, the B column, which corresponds to free variables. There will be many solutions. We don't stop. We carry through with back substitution. We still need to do that to find that solution, but the final solution will need to be expressed with pivot variables in terms of the free variables or as a parametric form. If, on the other hand, every column except for the last contains a pivot, then the system has exactly one solution, and back substitution will give you the solution directly. After we're finished with forward elimination, we know if there's no solution, if there's many solutions, or if there's a unique solution. As long as there are solutions, we keep moving forward, but keep in mind the nature of the solution. If there's no solutions, we stop. We can similarly phrase back substitution as an algorithm. back substitution, we begin with an augmented matrix in upper triangular or row echelon form. We work from the bottom to the top, moving from right to left, starting with the pivot in the last non-zero row, eliminate upwards, scale by the value of the pivot so that we have a pivot entry of 1, move up to the second to last non-zero row, do the same, move up, do the same, until we get our row canonical form, or reduced row echelon form. Similarly, as we did for forward substitution, we can phrase that in sort of clear, rigorous language that can be directly translated into a computer program. Working with our m by n plus 1 augmented matrix in upper triangular form, we start with row I equals m, the last row, and repeat until we reach I equals 1, the first row. If row I is all zeros except for the last column, there's no solution, stop, don't move forward. If row I is all zeros, that's kind of a meaningless row. It's a row that doesn't have a lot of information in it. We simply move up to the next row, demonstrated here. Otherwise, if we have non-zero entries, but not only in the last column, we select J as the column with the first non-zero entry, that is, it's the pivot. We scale that row to make that pivot entry equal 1. Divide by the value of the coefficient. After doing that, we use that value as a pivot to eliminate upwards, and we have a rule replacing RK by the appropriate coefficient by Ri, replacing Rk for all of the k above I, and then move up a row. Do the same thing. Repeat doing this until we're done. This gives us a formal representation of the back substitution process. You do not need to think about it in these terms, just as you don't need to think about the forward elimination in exactly these terms, but the operations that you're doing should correspond to what is being summarized here. Just as with forward substitution, there's some checkpoints, or forward elimination, there's checkpoints. The same thing there is for back substitution. Once we have this reduced row echelon form, we can look at these various points. If every column except the last contains a pivot, right? That is, every column has a pivot, the last doesn't, then the system has exactly one solution. When this is the case, the last column has that solution directly in it. If there are columns except the last that do not contain a pivot, that means we have free variables. We have multiple solutions. If we translate back to equation form, we can easily write a general solution with almost no effort, writing this general solution with pivots as functions of the free variables. Finally, if after doing back substitution you end up with rows that have a non-zero only in the last column, the implication is that the system has no solution, but you should have already caught this. If you get this result and your upper triangular form that you started with didn't have this case, this is a flag that something has gone wrong. Right? You should have been able to identify no solution in the upper triangular form, not only after doing back substitution. Okay. So just a couple of final comments. This framework of using augmented matrix, I believe, is a very, very nice, clean way to perform Gaussian elimination to solve linear systems. It's simpler to write, it's easier to read, and so on. Please use this approach for forward elimination. If you feel less comfortable doing back substitution at this stage, you can shift back to the algebraic equation form to do back substitution. I do think it's good to get the practice doing back substitution in augmented matrix form. We will find with some later applications that we need to do that, but it's not absolutely required if you really just don't feel comfortable doing those back substitution steps in that framework. Right? I should also note that it is possible to solve linear equations, systems of linear equations, without following the strict rules of Gaussian elimination. You can do it without exchanging rows. When you find somewhere where you should exchange rows, to instead use a different entry to do the pivoting and things like that. I don't think you should do this. It can get you a solution, but it's very easy to make mistakes. And more importantly, you lose a lot of the connections that we're going to be discussing later on. In the next units, we're going to be discussing matrix inverses, LU decomposition, and other things. And those connections exist when we are doing Gaussian elimination as we have discussed here. So stick with clean Gaussian elimination. If you reach a point that you need to do the exchange, actually do the exchange so that you end up with a formal row echelon form after elimination, forward elimination, and a reduced row echelon form after back substitution. All right. There are accompanying videos for this unit where we'll go through worked examples, both using the augmented matrix form and using system of equations form if you want additional practice. Otherwise, the primary content of Unit 3 we've finished with. Thank you and goodbye.